All right, well, welcome to my workshop. So I'm Professor David Minton at Purdue University, and how many of you saw my talk on Monday? You did? Okay, and I saw you guys. Okay, so on Monday I gave a talk mostly on the half of my work that's the n-body dynamics and origins of things, collisional fragmentation. But about half of my work is actually in cratering, and as I justified that my interest in this, I guess justifies the point. I can work on whatever I want. I got tenure. My motivation for exploring cratered surfaces is that they are the fossil record of small body dynamics. And I've learned over the years that they're more than just holes in the ground, made by space rocks, which is already kind of pretty cool for a hole in the ground. But they actually are one of the key geological features that planetary scientists use to sort of understand early solar systems. They're ubiquitous across the solar system, and they are fascinating in their own right. So, so because my Tuesday workshop had the benefit of the talk that people saw, and they didn't have that to kind of intro this, so I thankfully one of my grad students just taught a class for one of our classes at Purdue, and updated some slides that kind of date back to some that I put together for the same class that I taught. So she shared them with me, and so I'm not gonna take the entire time on this, but I want to kind of start with the basics so we're all kind of on the same page. Let me just get a sense. You're what major are you? You're from?
I'm applied mathematics.
Applied math, okay.
Minor astronomy.
Okay, all right. So have you if I say production function and crater size frequency distribution, are those words that ring a bell or?
Yeah.
Up to you. Okay, all right. I know who you are.
Yeah.
Or
I'm Ruby Fulford. I'm a second year grad student in LPL. I'm in the same research group.
okay, which group are you all in?
Jeff Andrews Canada.
Oh, okay. Jeff. Yeah, he's one of the greats. I really admire him. I was really happy when you all got in here. And so you're sorry, name just went right out of my head. You're
Ruby.
Ruby. Okay, like a Dr. Who. Okay, all right. I can do that. Right.
And I'm Gabe.
Gabe. Okay. And so what do y'all work on with Jeff?
I do lunar gravity mostly.
Okay.
I like the kind of overall motivation of my research is like probing the really early Martian environment,
Okay.
pre-Noachian, early Noachian. But I've actually been developing my own model that maybe it's kind of similar to Cratermaker. It like populates like the input surface with craters,
Yes.
and with like a little bit of erosion as well to see how Martian landscapes will develop.
All right.
So I'm
good.
interested in like
Nice.
seeing what else is out there. I think it's like different enough that I'm not completely right.
Yeah, no, these are I've seen them. Actually, Shane Byrne had a student who built one a few years ago. And I'm not the very first to do this. In fact, the code that I'm going to show you is based on a code that Jim Richardson was also an LPLer here before my time. Had actually wrote as a homework problem solution to Jay Malash's planetary services class that then became this became this eventually. So this actually, the code you're going to see today has its origin in a LPL core class in the late 90s, early 2000s. So so yeah, they're not unique, but I will say that one of the things I've learned is that these things seem conceptually easy. Jim's original code was just circles drawn on a grid. But the more you look into it, the more tricky it gets. So I'm happy you're working on it, but you're actually part of like a person I could imagine recruiting to help with this. So all right, so keep you in mind. All right, so I want to go through some of the basics. I'm going to go through this quickly because they're mostly planetary people, so probably know that what's the biggest difference between the near side and the far side of the moon by eye?
All right.
Yeah, so what does that mean? Okay, we're having a workshop about Cratermaker.
More craters on the far.
Yeah, right. Now there's a funny thing that happens in like you know, if you ever teach any of the undergrad, your TA undergrad class, you're going to come across like undergrad students who are not as have the knowledge base to go through here. So one of the sort of popular misconceptions about the moon is that the reason why there are more craters on the far side, the near side, is that the near side face the Earth, therefore it shields the moon from craters. Of course, that's not true for a number of reasons. One is you should try the exercise of getting a tennis ball and a basketball right to the Earth and the moon. Get students to tell you how far apart they are. You keep telling them you're too close. You keep telling them they're too close. You keep telling them they're too close until they're like 30 feet apart from each other. But it's also just that actually the near side and far side have roughly the same cratering history, but Mari came after and filled up and erased all the craters. So right away we can actually see the main processes that we care about is craters accumulate on the surface, and then things happen and erase the craters, and so that the age of the surface more or less maps to the crater number density on the surface, right? So there's a crater. Okay, this is we have simple craters, we have transitional craters, we have complex craters, and peak rings, multi-ring basins, which getting into the realm of actually multi-ring basins might actually be mostly a lunar phenomenon. You'll see we see this scales, we start to see like real fundamental differences in different planets for this. The classic multi-ring Oriental basin is one of the few big multi-ring basins that hasn't been degraded so much on the moon, so we can actually study it and report for that. If you a lot of people who study the mechanics of craters use things like IceSail, hydrocodes, where you can actually model the impact into a fluid, because at the scales we're talking about for these events, rock behaves more like a fluid. So use fluid codes to model this. So the people who do this kind of work, this is actually a dean. We just talked to her a couple hours ago on Zoom. So she was actually a student at Purdue who did some of this work with IceSail, study how individual craters form. What are the processes that create a crater, modify the surface, move material around, and that's all great. That helps us to really understand the sort of physics of individual craters. But what I actually, and here's just an example of creating these multi-rings. It's really you think about like what you're seeing here. I mean, look at the numbers on the axis at kilometers, right? It's like mountains of material going up and down. Must have been really awesome in the original sense of the word to actually watch these things. If you could. Okay, this is class. Okay, so what I actually, where we're going with this is not really thinking about the mechanics of individual craters, but what happens when you populate a surface with lots of craters. So one of the primary tools that craters use is for figuring out the age of surfaces. So this is Gale crater. Who knows why Gale crater is chosen? What's Gale crater's significance?
Curiosity.
Yes, so that's a Mars rover is down in there, and it's the Curiosity. So we want to know, like, how old are things? Geology has these sort of commonsensical principles that we give fancy names to, but they're actually pretty obvious. The principle of superposition and original horizontality is just a real basic thing where younger things go on top of older things. And if you see a layer in one place because these things are happening on a gravity field, things tend to settle into flat surfaces. So we have this idea of like a time scale maps to a depth scale. This is the basis of a lot of our geological understanding, right? So the same thing happens on crater surfaces. Although it's the principle of superposition, you have to really kind of, because we don't often have like ground-based observations, we look down on the surface and you have to make inferences. So we know that like, the story of the Mari coming later is seen right here on a image like this. We see the heavily cratered highlands, there are higher elevation terrains off to the upper left. was a lava flow that came later, filled in. There probably were many craters populating that surface, but then they're all covered up by this lava that flattens out later. And makes the surface, and then fewer craters accumulate as you're kind of starting surface over scratch. So we know that this is a continuous process that occurs. And so one of the things we can do with our codes is to sort of model what does actually one of these surfaces look like over time. So this is an example of a simulation from the progenitor code to Cratermaker. This is a code called CTEM, the Crater Terrain Evolution Model. CTEM was the workhorse code of my research group for about a decade, but it was severely limited in a number of ways. But it's also really cool in a number of ways. So I'm going to show you this because this is just an example of what we're aiming to do with Cratermaker eventually. Well, not quite there yet, but this is the, if you were to sit in, let's say a mare flow formed on the surface, you're able to sit there and watch time pass for 4 billion years. This is kind of what the surface would look like at this scale. So this is the moon is not a dead world. It seems like dead to a human to human timescales, but if you had a time scale of a demigod, you would look like it's raining into mud. I mean, that's basically the impression I always get when I look at this. On the side, there's an exercise I haven't gotten around to it yet, is to model one of these at a really small scale to show what happens to like the Armstrong's footprint over time, because it won't actually last very long. All the Apollo stuff will not last geologically very long because it's going to get chewed up by this rain of rock forming on the surface. But you already see some of the processes at work here, like the craters sort of look like they're kind of melting, they're degrading. That's a really important physical process occurring that we want to be able to capture and model. We have observations of these surfaces, so we can actually compare, how does the real surface compare to our model surface, and see at least at these scales, CTEM is able to do a pretty good job of this. Now, craters are, for a number of people, researchers are really useful for counting. And so I want to kind of walk through what we mean by crater count. Has anybody here actually done a crater count of the surface, like a lab or class or something? Kind of. If you have counted them or not. I mean, maybe just like looked at,
I guess I feel like I haven't done a like.
Maybe not a research grade.
Yeah, not like a research grade.
But have you had an exercise in a class where, like, all right, you need to count this and then fit it to a production function or a micron or something? Okay.
The chain stuff.
Okay, yeah, Shane would have been the guy that. Okay.
And
So-
able to do this as well. Yeah.
All right, so you all have been through this before, so I'll try to go through quickly. But this is actually an artificial terrain that a student, summer undergrad, worked with us to do. So you count everything as a circle, right? And then I made this slide when I had little kids. The kids are older now, but back then I had little kids. So you must count the craters. It's really slow if you have to go in between a little bit.
Yeah, that's not the hard of it.
Okay, then you basically create a size frequency distribution. You order the craters from biggest to smallest and index them so that the largest crater is number 1, second largest crater is number 2, third largest is number 3, so on and so forth. And that just automatically gives you a cumulative size frequency distribution, the number of craters greater than a given diameter at that diameter, right? And crater terrains typically take on the appearance of these power laws. This is a really, actually a pretty good model for size frequency distributions of craters, even though there's an old adage that everything is linear when plotted log fat magic marker. So they're mostly power laws, but there are deviations. You actually see one here at the small scale. This rollover here is actually, so the computer program that generated this terrain actually made craters all the way down to small sizes, but it's a well-known effect that when you start getting the craters that are a few pixels in size, they get harder to identify. So we see this in real data and artificial data. This is a classic rollover due to resolution effects that occurs. So it's a deviation from power law right there. You see there's a little bit of deviation at the big end, but that's get into the statistics in a bit. Okay, so the basic principle, again, this is a commonsensical thing, that the basic principle of crater counting is that you start with a crater-free surface at time 0, and then you populate it with craters of all different sizes at some other time. And then you can start to ask about, what what the craters of different size, how many craters are there of different sizes? So this is the size frequency distribution that they're building up, right? And then you fit that to a power law. That's your size frequency distribution. Okay. So there is a limit to this, and this is a important process called equilibrium. This comes right out of the Jamal Losh's textbook. So if you were to model track the total number of craters over time at a given size, it goes up and up along this what's called the production curve. So the production function is what's often used to describe the rate at which new craters of a given size accumulate on the surface. And there's a point where you start to max out. You start to see no more craters being accumulated on that surface. Now I've highlighted here, there's a line where that occurs, which we call equilibrium. And this is a bit of a hobby horse of mine to make sure we get this terminology right. So this is what's called equilibrium, and that is a distinct concept to what's called saturation or geometric saturation. Okay, so who here has had a professor who has made this distinction for you? Or have you heard of saturation, equilibrium are the same thing?
I would have thought that.
Yes, okay. These terms were actually coined by a guy named Don Galt, who was an Ames scientist, as an Ames scientist back in the Apollo days. And people kind of ignored his terminology. These are actually really distinct things. I'm going to explain what they are, because I think it's important for when we start to see why it is that modeling this stuff can be really tricky. Okay, geometric saturation is a concept. It's a hypothetical scenario in which what would happen if you were to completely fill up a surface with circles, right? So if you were to take a surface of a finite area and pack it up with circles, there's a maximum number of circles that you can actually fit on that surface for a given size circle. And if you were to actually, now this is a bit of an artificial construct, but it is mathematically the most packed you can put circles onto a surface. So it is an absolute upper limit how cratered a surface could be. And nature never gets that close because nature doesn't arrange craters on a surface into this close packed hexagonal, crystal structure. But it's a useful concept because it really gives you a point to which to compare against. If you do this for different size craters, that you get a slightly different number, a significantly different number. And so that gives you like a baseline to compare against, a mathematically defined upper limit that you can then compare the reality to. So real surfaces don't ever reach this. They don't even get close to this for the most part. And that's because of degradation. So there's a couple of different ways to degrade or remove a crater from the surface. One is that you can, we call it cookie cutting. Just a big crater hits and erases everything underneath it. And that's, again, a pretty straightforward thing. There's another process which is more relevant to what we're going to see for the sort of small scale Mare surfaces. That's called sandblasting, or really diffusive degradation. So you can actually take a big crater and whittle it away by the effects of small craters, so that it sort of melts away into something you wouldn't recognize as a crater. This is what dominates those scenes that we saw earlier. Ejecta can also bury craters, so that when you actually look at a real surface, you actually see that the equilibrium line is a little bit lower this. And actually, there was a big study I did to try to work out, why is it that craters max out at that equilibrium, which is below saturation. So to watch this surface, we're gonna right here. I've got a plot of this is a classic size distribution of craters at a place called Sinus Medii. There's a patch of Mare right in the sort of 0, point of the equilibrium. So Sinus Medii is the meridian and the equator. So it's like 0, 0 or close to it. Shoemaker, who was a time LPL guy, worked on the Apollo missions. Actually, I think this is his data. Yeah. So in our model, you basically, the red is the production function, and then the blue is the craters, and you can see that their model, we can start to match that. Okay, so when I say there's a distinction in equilibrium and saturation, I think it's really important to look at what that is, right? So remember, saturation is where you completely pack a surface with craters, right? Okay, so I want you to look at the craters that are roughly like 10 meter size, like this, right? Like this size. So how many of these craters do you see roughly this size?
Or 15?
Yeah, so we can kind of say, here's one, maybe here, this is just a couple, right? Yeah, so we got a handful of like divots and things. But it's like there's a lot of space in between, right? Like you can imagine putting more craters there, right?
Yeah.
This is actually an equilibrium. This is the most craters you'll see of this size on a surface of this scale. You don't see more than this. You could put more on there, but you don't. That's why equilibrium and saturation are different things. Saturation is when you saturate you fill up the surface, and maybe not just the closed packed crystallographical structure is not physical, but you can imagine just like randomly inserting a bunch of craters here, you could still put more craters onto the surface than you have.
This is like saying using your production function and the physical processes, by the time the next object of this size or next crater of this size is formed, one of the other ones of these would be erased.
Yeah, so you imagine that equilibrium is when we think about it in physics, equilibrium is a thing that's where you have a source and a sink, right? So you have a process that's sourcing craters, you're adding craters to a surface, and you have a process that's basically degrading those craters over time. And what happens is that when as these craters are forming, you can kind of see there's a sequence of degradation states, right? You have fresh or nice and sharp, and then you got more degraded, more degraded, more degraded. So there's a sequence of time as you're cratering the surface, the old craters are eroding away to nothing. And at some point, you erode away so much that you don't recognize it anymore. And the rate at which the craters are degrading like that, relative to the rate at which craters that size are forming, when those are in balance, that becomes equilibrium.
So
It's a dynamic process.
a cheeky question would be like, how long until the next crater is formed? And you could answer, it'll be the same time, and by the time that
Yeah,
crater
right.
disappears.
And the thing that I think when people often, I have some like hangups about this. We're going a little rant here.
Yeah.
When people who ought to know better, like crater counting people and people in the field, professionals, talk about, equilibrium is what happened when you get so many craters that each new crater erases a crater of that size. But the two events, the next crater and the erasure of the old crater don't have to have any causality connection to it. It's a time scale.
What always confused me
Yeah.
about it, like I knew intellectually that saturation and equilibrium weren't the same thing.
Yeah.
But I feel like the things that I've read,
Mhm.
it's been worded kind of like that,
Mhm.
and
Yeah, it's one of my like missions to correct these misconceptions,
when
right?
I see this, I'm like, well, obviously,
Yeah.
what are the odds
Yeah.
that like the next?
Right.
C
So
crater
it's not
will-
like the next crater is gonna have to hit one of these.
Yeah.
If the next crater hits here, and then the time it takes to go from this crater to the next, this crater will have eroded away to nothing.
Right,
So
because
they're not necessarily causally connected, it's just, that's the amount of time it takes, right? And this is why equilibrium is not really, the processes that lead to this are not straightforward. It's not just accumulating craters on the surface. You have to understand what is the thing that's actually degrading the surface, right? Degrading the craters. Okay. Let's see. Secondaries, we actually have a project going right now to actually model secondaries better. I don't want to belabor it too much because it's not in the code yet. Let's see, let me go ahead. Let me talk a little bit about how we actually turn craters into ages, because that's another place where there's a lot of misconceptions about what happens here. Okay, so we like to use craters to figure out the age of surface. But in order to do that, there's actually something we need. We need a calibration for that, okay? The way in which this has been done is that, and this can really only be done thanks to the Apollo program, and with some help now from Chinese, China. But it was pioneered by the Apollo program, is that if you find a surface for which you can actually count the craters on it, and then you bring a piece of that surface back and figure out its age, you can basically put a pinpoint on this curve of age versus number of craters. And you say, at this age surface, you have this many craters. The people who kind of worked on this in the 70s and 80s were Gerhard Neukom, Germany, and Bill Hartmann, who's on the street, probably painting pictures of mountains right now. Actually, the sun's probably a little high for him. He'd be out in the evening, like painting landscapes. You ever all met Bill Hartmann? Has he come by here at all? He's a PSI.
I don't think so.
He's like one of the very first people at LBL that came here as a researcher in the Apollo program. He was just
Stayed at Don Davis's house though.
yeah,
That's about it.
yeah, okay. Yeah, Hartman's an interesting guy. So this is like one of his major contributions to the field was to work out the science of this, right? So Hartmann and Neukom kind of together. So the idea is that if you are able to do this with a number of surfaces, you can sort of build up two kinds of curves. One is what is the size frequency distribution of the production, like how many craters at a given size are forming on the surface, and then how that's changing with time. Now there's some assumptions that have to go into this to make this all work. One is that you have to sort of work out what the shape of this production size distribution is from observations, and then you have to assume that shape of that doesn't change with time. So you kind of slide that in time, barring equilibrium, and build a picture. So the thing that Hartmann does to show this is build what are called isochrons. This is really his thing, the lunar isochron or crater isochron plots. He kind of developed this technique. And it's a way of sort of really quickly figuring out the age of a surface by using these principles. There are three principles. One is that the size frequency distribution is, the shape of it is fixed with time, that the amount of cratering follows this curve that's been calibrated by Apollo samples, and then there's an equilibrium line, and he actually calls it the empirical saturation, right? But it's the equilibrium. So you see it's written saturation here, but it's the equilibrium line. So that's the place where you stop being able to tell the age of a surface because the number of craters doesn't change. So you can see that you get this like flattening up here. Okay, so this is a really, really powerful technique because you can do this by hand. You can actually, in fact, when I was here, I did a little lab, a planetary surfaces lab with Bob Straumann put together, where we just did this by hand. We actually counted on these like Viking images and drew dots on a plots like these to figure out how old they are. Okay, I love this. This is a great example of how it can be worked. This is the crater Giordano Bruno. Anybody heard of Giordano Bruno before? Yeah. There was in the heady days of the 1970s, there was an idea put forth by somebody that there's this event seen in like Islamic mythology of like the moon being split in two, and there was also like there was a monk that said they observed like the moon like split in two. There are these like stories in the medieval, like 1,000 years ago, something happened in the moon to split it in two, or seeing this flash light. So he said, well, this is like the youngest, freshest looking of these big craters on the moon. Maybe what they saw was the formation of Giordano Bruno. It would have been big enough to see from Earth, and proposed that this was that. Well, when the Goya mission happened, we actually got some really good high resolution imagery of this, and so a group of researchers decided to test that hypothesis by counting up the craters on top of Giordano Bruno and using isochrons to actually work it out. So here is from that paper, and so you can actually see the squares are the crater counts of these terrains Now, the way you do this is you count the terrains, you have to divide by the surface area to kind of normalize it. So it's a cumulative number per unit area. And then you fit that to isochron. You can see that Giordano Bruno is actually between 1 and 10 million years old. It's probably around a couple million years. So it can't be, no monks were around 2 million years ago to watch this. Okay. We're still working on this. So there's all these new data to basically fit these isochron curves too. So this is still an ongoing process of doing this. Mars is, let's mention Mars. So the names Hesperian, Noachian, Amazonian, those are actually defined in terms of crater counts. There are terrains which exhibit those the sort of type locale, the Amazonas basin. There's like places where you go and say this is the quintessential type, but the actual division of those geologic time periods is based on crater counts. It's the number of craters per unit area. Now Mars is tricky because they're more than just, right, the degradation processes on the moon. You have wind and weather and maybe even rain and snow and stuff, glaciers, and you go further back in time. But this is actually what these are. And so this Mars isochron is based on taking the lunar isochron and just imagining that it's the same population of impactors hitting the moon and Mars with the same function. And you correct for different gravity, different impact probabilities, if you assume things come from a belt-like population, yada, yada, yada. And so these are extrapolations of the Apollo era lunar chronology function. So always keep that in mind, that even though the Amazonian, Noachian, and Hesperian have precise definitions in terms of crater number density, those crater number densities do not have precise values of time, no matter what people like to think. So the Amazonian, the Hesperian, Noachian boundary at 3.9 billion is a model that's based on a whole heap of assumptions we have not tested fully yet. So we don't actually have this kind of calibration for Mars. So anybody who works on Mars should always keep that in mind. I think there's a paper by Jeff Andrews Hanna and Bill Bocke a few years ago about this weird gap in the basins to rest the craters. My opinion of that paper, and I know Bill, I don't know about Jeff, I know Bill disagrees with me on this, but my interpretation of that is because we actually don't have good chronology for Mars. And my work on the moon suggests that actually the Noachian Hesperian is probably much older in time than this. That gap is an artificial construct of using the wrong chronology function. That's my 2 cents. So I haven't proved that yet.
Jeff agrees with that specifically, but he does. I know he would agree that the chronology of Mars is like iffy.
It's very iffy.
There's a chance that we guys have it all wrong. Like for my model and other things, it's like I feel like I kind of have no choice but to like work with what we have.
We all do. Yes, we all do.
With the understanding that maybe this is completely wrong.
Yeah, I'm right there with you. I'm working on projects that I'm hoping will sort of quantify that a bit, but anyway, we can talk more when we're not trying to do a job on code, but I'm happy to talk. Is Jeff around this week?
No, he's on sabbatical right now.
Oh, he's on sabbatical too. Where is he actually? At work. He's worried. Okay, all right. Yeah, that's where I was going to do sabbatical. They didn't fund my proposal for that. NASA. Okay, so that's sort of an intro to this. So let's get into the code. Okay. Now I told you I showed you some really nifty movies of CTEM. Let's talk a little bit about Cratermaker because Cratermaker came out of a use of CTEM for a number of years, illuminated a lot of issues with it. CTEM used this flat surface domain with a repeating boundary. It was entirely written, it was actually originally written in Fortran 77. I upgraded it at least to Fortran 90. Had an ideal front end for a while. We eventually wrote a Python front end. It's incredibly difficult to use, has lots of knobs and things that you have to turn manually to make work. And it's a pain in the butt to use and would take me like a year to get a student up and running and to be able to do anything with it. Very powerful code, but like a lot of things, it's a little long in the tooth. So 2 years ago or so, I embarked on a mission to modernize the code, and that effort has led to this Cratermaker. So I'm going to tell you, Cratermaker is still in alpha stage. It does not have all the capabilities of CTEM yet, but it actually has a lot of things that can do better than CTEM. And I think it's actually really useful for a number of ways. And I want to hopefully demonstrate some of its utility to you all today. Okay, so most of what I do, if you were here for my yesterday's thing, I had like a set of like notebooks to try to work through. I have one notebook here for this. For the most part, though, I've been having, me and my students have been writing these documentation pages and example scripts, full example scripts. So I actually have a ready-made set of like examples to show you. And so rather than trying to like have everybody kind of go through like step by step, I'm going to intro you to like how to like set up Cratermaker, and then we can talk about like the different components, how to use those, and we can even pick out some examples and we can walk through them and show you the logic behind them. But I've tried, this should hopefully be a little easier to get running than Swift was, because the dependency issues are way less. So let's kind of start from this. All right, by the way, any questions about the science of cratering before we jump into code? Okay.
I'm sorry, I actually did have a question.
Yeah.
So does this kind of code take into account effects of seismic shaking and removing
Ah.
all the phrases?
Jim Richardson was all about seismic shaking.
Yeah.
He actually wrote the code in order to model seismic shaking on
Yeah.
asteroids. So actually, one of the first things he did with the code, other than the lunar problem, was asteroid Eros, because he got some funding from Gear Shoemaker. So seismic shaking was like his jam. So CTEM had a seismic shaking model, and when I was working with them on the lunar project, so what seismic shaking does is it creates a diffusion, Doppler diffusion. Again, there's poor constraints on a lot of the seismic parameters, but you can tune things to kind of get it to match, and fix problems like asteroid craters. The thing though is that seismic shaking has a very strong gravity dependence. And so when you go from something the size of Eros up to something the size of the moon, the seismic shaking doesn't seem to contribute very much to degradation at the scales that are relevant to like crater equilibrium and landscape evolution. The moon's just gravity's too strong. So sine waves, they do cause degradation. Actually, Carolyn Vanderboger and Munster has some really interesting work showing that there's like the meter-sized craters near these scarps in the South Pole are oddly smooth and don't have craters. And she attributes that to actually seismic shaking. You know, the scarp is actually still moving. So you actually get these little moonquakes, and we actually see seismic signals of moonquakes there. And so it actually locally erases craters along the scarp. So that's a neat result that has seismic shaking, but that kind of affects things at like the centimeter meter scales, right? So it's not something that seems to matter for the large scale moon.
Right, and you guys are not using it yet for.
Not yet, no. We are not. I have some. So one of the things that makes Cratermaker better than CTEM is the ability to read in. You can actually it models the surface as a mesh. So in principle, we could throw in small bodies and
Right.
have meshes. We're just not there yet. It's still too new of a code.
Okay.
To get quite there yet, but it's on the roadmap.
Makes sense, yeah.
Okay, so we lost one. So I know they should have sent this out. Have people downloaded these codes, ParaView and QGIS? I think the ParaView is the one I want to make sure you have installed first. Okay, so you'll have the GitHub, right? GitHub repository they sent out thing. Okay. I don't need you to clone it quite yet. You can, but I would like you to at least download ParaView. That's one that I'll show off. You kind of start with.
Is there a specific version that you prefer us to download?
I have version 6.0.0 on my computer. I think it just came out like a few weeks ago.
Okay.
I was using 5 point something up until.
I don't know if
You have it, this GitHub?
was the GitHub.
I don't think it would be ever. Let me.
Oh,
Here, I can send you.
it just
Schedule.
This is this.
okay,
I'll send it to you.
thanks.
That'll take you to this page, and then that'll get you to the ParaView. How about it? We will find.
Again, let people have a chance to
And,
peer review.
and I need QGIS as well.
Not yet, QJ, so. This is the problem with code that's sort of active development. I only got the QGIS formatted stuff working like a couple weeks ago. So it's still pretty new. I want peer review is a little bit more user-friendly. It's not very user-friendly, but it's more user-friendly than QGIS. So let's start with peer review. And if we're being really ambitious by the time our time is up, we'll maybe look at how to analyze. Has anybody here used QGIS or ArcGIS? Yeah, okay. You're probably more familiar than I am. I've only just started learning it this summer. I have used ArcMap. I actually did some Cratermaker studies in ArcGIS, but I like QGIS because it can run on my Mac. I have Windows. Right? Okay, we're all downloading peer review. So you have peer review yet?
Peer review just instantly crashed without
Oh, no.
opening it, so I will, that's it, I downloaded it 2 years ago probably, so I'll
Okay, yeah,
get a new version.
get a newer version maybe.
Yeah,
Review so long.
Very long time to download.
Yeah. I'm about
Oh,
the
yeah.
same issue.
Oh, okay.
I happen to already have it because I was in a class that used it.
Oh, really? So it was funny is that my client, I saw it in the context of a climate model, but all my climate modeling colleagues haven't heard of it before. So what class did you use it in?
Mine was in like a landscape evolution model.
Ah, okay, all right, that makes
It's
sense.
like fluvial processes.
Is that John Pelletier?
Yes.
Yes, okay. You wrote the book on it.
Literally.
Literally. When I was a student, he actually gave a great colloquium on Greenland, like his modeling of the Greenland ice sheet. Okay. All right, well, if it's taking a long time, just let it download background. We don't need it right away. I just want to make sure sort of at least get the process going. So I would like you to also clone this workshop GitHub into your local machine. There's one example on there, okay? And I just updated it like 20 minutes ago. So if you previously did, make sure you get pull down the latest. Okay. So if you were here from yesterday's, not everybody was, but if you were, it's the same procedure to kind of get a environment started. So I decided to just keep an isolated virtual environment for Cratermaker. So have you done that? This step? Something like this?
I instantly made an event, but I haven't done the Python kernel for them.
Okay.
Yeah.
Why don't we, because I know if for those of you who were here yesterday, it took a little bit of time to get everybody caught up to this stage. So I'm gonna let everybody sort of catch up. Everybody, the wonderful thing about Python is it's very flexible and allows you to run multiple versions and have all of these options for different kinds of styles of keeping track of things. The really terrible thing about Python is it's very flexible and it has like, as many ways of keeping track of things. Conda and VNV and poetry and UV and UVX. I've yet to have a Python-based tutorial thing, either as a on this side of the tutorial or on the other side, that this went smoothly. So
It's always such.
let's this works on my machine. 50-50, it works on yours. So let's see how everybody's doing getting up to this point.
Stupid solid.
Oh, you don't have Git. Oh, you've got Windows. Oh, boy. Okay,
Yeah.
Windows should work, but you're gonna need,
USL?
Somehow mine worked on this.
you probably have Git already. There's probably some, yeah, PowerShell. There's some tool. I know there's a set of tools for this. I once installed it on a Windows machine long ago, but I don't use Windows often. The Cratermaker should work on Windows.
I have Cratermaker from like the pip install, but
Okay, but you don't.
I don't have
Git.
I don't have the
Okay.
Git at the
Um,
moment. I could
we
probably.
might have to just Google how do I get
Yeah.
Git on a Windows machine.
Yeah.
And follow instructions.
The same issue with that IPy kernel that we were having yesterday
Yes.
for some reason. The pip install worked, but I'm stuck here again. I don't know.
We did fix it, didn't we?
We did, I'm
And
not.
I did a bunch of like magic steps.
Yeah.
Okay, so one thing is I think it's using the wrong IPython. That's one problem.
Yeah, I had to pip install IPython and IPyKernel, so like,
Separately?
Wait.
Okay.
and then it worked.
I always like to. Just as I don't have that message. Drives me nuts. You leave a virtual environment alone a couple days and they upgrade to.
Yeah, pretty good, yeah.
That machine. Okay, so, okay, you can read.
Let me try that.
I'm gonna mess it up because I'm so used to using Z shell calling it. By the way, if anybody user or back user, Oh My Z Shell is a really wonderful tool. I love Oh My Z Shell. I get all my students in my lab to use it. Has I think the best history recall tool of any of the Linux shells. And it has a really nice formatting options. That's just my opinion, the religious argument. Made.
I see that you have BTK as one of the
Yep.
dependencies. Have you looked into PyVista at all? So that way PyVista ParaView is built on
Yeah.
BTK the same way that PyVista is just a Python application.
Right, I did, at one point I did. There was some,
It's might reduce your dependencies with like use it outside.
I'm just trying to remember, there was a reason why PyVista couldn't do the thing I wanted to do, but VTK could. And it's been a while.
It's also like they've been under active development. I mean, every time I go back to it, they have like
Okay,
new tools.
yeah,
and so
yeah, it could be that things have changed since I first looked at it. I'll look at it again. This is really, the only reason I have the VTK in there is because the default is to output VTK format files, so that you can read them in by parity.
But yeah, so I guess like maybe you might be interested to.
Okay, I'll look into it again. I do remember playing around with PyVista.
So that way you could just do everything just from your Python scripts rather than having to output or.
Oh, yeah, I see.
Data
Yeah,
to, and then open it there.
Yeah.
You could just have.
That's true, that's true.
Yeah.
One of the things that's on our roadmap is to consolidate some of the tools, so that we don't have to rely on third-party software as much. Although a lot of my colleagues who do this sort of stuff use GIS tools, so that's why it was like motivation for me to actually get GIS formatted outputs. Many things to do. All right, so Git is putting.
No, that's not it. Okay.
All right, so you got that.
Telling me that
Okay.
Okay, it's good.
Python 3.13 is not a.
Oh, you may have to download that.
I have.
Or just use.
Oh, 3.11. Are you just 3.11? You.
12.
In Windows might be a little different than Mac, is how it calls it.
Yeah,
Um,
I kind of forget how it. If I just say pi, it works.
Yeah, sure, just do that. As long as it's, like, I think the lowest one we support is 3.11.
Okay.
There are some dependency issues where certain of the packages for, especially for the outputting stuff, they deprecate old Python versions. You actually got it.
I don't know if I activate the environment.
Yeah, I'm unfortunately not as familiar with Windows, so
I've only ever made like Conda environments.
you can do it with Conda. You don't have to follow my directions. If you know how to do it with Conda, you can.
I know
do
how
it.
to make an environment in Conda. I don't know how to do the other.
Oh, you don't have to do this in Conda because, well, maybe you do. If you, do you ever use like the Anaconda, like actual app?
Yes.
Yeah, I think you can actually just have Jupyter run from inside there.
Oh, yeah.
Yeah. So just do it. So basically, whatever, like if you were to install NumPy, it's the same thing. You build something, install Cratermaker, just like you would build and install like NumPy or SciPy or whatever Python package. It's just on PyPy. So I just, those are that's the way I do it, but everybody's different.
Okay, well, I'm still like.
I know, this is why I knew it was gonna happen, that
Yeah.
we're gonna spend like half the time getting everybody's on the B&B, and nobody used poetry here. That's pretty good, because I love that, like, poetry guys, like, poetry solves all our problems from Conda and B&Bs. Then like a year later, UV solves all our problems with Conda. It's like, what happened to poetry? Anyway,
What is code?
Working.
That sounds like really.
the
good.
thing that solves all the problems with Conda, right?
I'm jumping ahead now.
Yeah, that's fine. That's fine.
Are you sure you want to delete one file?
Yeah, say yes.
Sure.
I guess, yeah. That's a new thing I added, because I was tired of accidentally deleting things, but it does cause some annoyance. Okay, so, okay, once you kind of get, when you get to the stage where you can get a,
They have made my life difficult as well, because I think I'm running this onto the remote machine and I pair view locally, so I'll have to.
yeah, you have to download, oh, also, if you happen to have owned Cratermaker before this morning, I did do an update. Or if you even installed it before this morning, I did that, so make sure you do pip install upgrade Cratermaker if you've already installed it previously.
This cool little accuracy show tool on my remote machine that automatically identifies if I have a virtual environment in that folder or subfolder and asks it.
So, VS Code is supposed to do that.
Yeah, VS Code says this, but like this.
Yeah, for anything, yeah, that's a good idea.
It's fun.
So I know you're on Jupyter, you got Jupyter up and running. Are we, who's got like Jupyter Lab up and running, still trying to install stuff?
I mean, I have, like,
Let me see, because that looks like you had an older version.
I do have a older version, and
Let me see if I can upgrade it.
I've been having issues lately. Yeah, that's what did all that.
Oh, really? Okay.
I've been having the same issue with ISH tools where it's like not.
I wonder, is this a fresh environment, or is this one that you've used before?
This is one I've used before.
So I'd say, oh, it looked like it worked.
Of course it did.
Yeah, it's because I did it, and I had to make you look like incompetent, right?
Yeah.
It's the way it works.
Yeah.
Same thing happens to me, I'm on the other side.
Yeah.
My guess is, okay, so one of the things I've learned over the years is do not be afraid to destroy your environments. They're really not precious. So I like the V&V model where you just create a new environment for every project, because you really don't need to, because they really do degrade, right? There's lots of tools that they upgrade and things break, and it's really a pain to sort of get all your dependencies sort of synced up again. So I almost always just create fresh environments every time I use stuff, just because I just learned that don't hold on to environments. They're really not that precious.
I only got ISH tools working once.
Oh, yeah, well.
Me too.
Yeah, I know.
Good, so you're running good, all right.
Way more data than that.
Folks are the,
I don't know how to make this, I'm sorry,
okay, let me see. Go
I
back to
don't know how to make this
Anaconda.
environment in Honda.
Let me see Anaconda Navigator.
There's like,
I see.
this is so.
There is like a, environments. Okay, yeah, I see. Yeah, you can just create an environment. It's
I
called,
just call it that.
yeah, call it the Cratermaker tab, or, yeah, whatever you want to call it.
What is
Call
is V is,
VENV.
yeah, is that just the name of the environment or is that a special?
No, the name, well, yes, the name of the environment is VNV because that's just the standard way you call
Oh.
environments on local things. But my Jupyter kernel is called Tap Cratermaker. So in Conda, you could actually make a Tap Cratermaker or just a Cratermaker environment. Yeah, you don't have to follow my
Okay.
guidelines.
I was just confused because to some, I think I'm just forgetting how to do all this.
Yeah, no, I get it. So just make a Cratermaker environment. Make it use a newer version of Python if you can. Not 14, but yeah, 13 should be fine. And create that, and hopefully that will do it. You can, once you get into Jupyter, we should be able to.
This has been going through multiple iterations of processing creators, and it's getting a little bit faster every single time.
Yeah, because the creator is getting smaller.
They're getting smaller. Yeah, so.
I just now need to install Cratermaker in this environment.
Yep, you just have to pip install Cratermaker. once you get your environment up and going. Okay. And if you do happen to have gotten this far, go ahead and just run all the cells, and then I'll kind of go through what happened, because it does take some time, especially the last one.
Yep.
It takes a bit of time to run, so I'm just gonna run it, because we're making all the named craters on the moon in that. And then as this is running, once everybody's kind of done troubleshooting their environments. We'll
Any chance you could just email inside the
You know, you the Jupyter file? Oh, because
Yeah, you know what you could do is you could go to the GitHub and just download it.
Yeah,
You don't have to clone
should be
it.
able to get it from, yeah.
Yeah, just go to my GitHub and just download the repo. It's a set of files.
Robert, if your sim.
Yeah, just download that folder if you can.
Is your sim.run cell still running?
Actually, all you need are these two files. And then you're good.
So
man.
sim.run took about 2 minutes. But the next cell is taking longer.
The pandas cell?
The one, yeah, the
Yes.
one, so that one is actually, I'll show you that it's actually gonna generate all the named craters on the moon.
Right, this one's just.
How long is your sim.run?
You have to
taking?
say, yes. I'll explain all that in a bit.
Okay.
Do what?
Oh, no, I'm just asking, okay, how long? So I thought I would say, it's not. Maybe it'd be nice to know like what.
Yeah, well, you know what, I actually had it. There's a print statement
Yeah.
that printed the name of each crater and,
I
because it was
thought,
making like a huge long, yeah, so I usually run this stuff in scripts, not in a
Yeah.
Jupyter cell, so the Jupyter notebook, so that's why like, some of it's a little rough in Jupyter because I usually just run a script.
yeah,
But it's easier to show things off with Jupyter. Okay, so while that's running and you're able to download this stuff?
Yeah.
Okay, so I'm gonna kind of talk a little bit about how Cratermaker works, what's going on under the hood. So, Cratermaker there's a couple of principles that work when I built Cratering. So if you saw my Swiftest thing, Swiftest is much older. I started Swiftest in like 2019. I started Cratermaker in like 2023. So I learned like a lot of lessons learned from the Swiftest project that I turned into figuring out how to run Cratermaker. Just like I said to Swiftest, Cratermaker, I adopt the principle of everything has a reasonable default. So there are defaults for everything. So that first cell that's like sim, so when you look at this very first cell up here. Okay, when you look at this very first cell here, and I print the sim. So it's the call is just sim equals Cratermaker.simulation. Very familiar if you've seen Swiftest, same kind of style of class implementation. And you see it basically prints out all these sort of things. These are the components of Cratermaker, and it's showing you the default thing. So I am currently working on a counting module. It's not quite done. It's using my 2019 papers counting module. There's a morphology model that basically is what controls what craters look like on the moon. And the particular morphology model is one called Simple Moon. I have a postdoc who's making, named June Du, who's developing a realistic version of that. Our default production function is the Neuquem production function. The default target is the moon. It shows you some information about that production function. There's a projectile population that's invoked. This basically determines things like the velocity distribution, density of impactors. That's the asteroids, because that's what Neuquem's model used. There's a crater scaling relationship. This is when you have, for a given impactor, what size crater do you make? Because every time you create a crater in Cratermaker, you also create an impactor, or vice versa. If you create an impactor, it creates a crater. So you need a way of going from simple, from the crater, the asteroid impactor size to the crater size. So the particular scaling model is actually unique to Cratermaker. It's based on one the CTEM used, which is based on Holsapple's model. It's a pi scaling model with some parameters that Keith Holsapple published in the 90s. There's a difference, and I can show you an example of what's different. So this is actually a rather unique crater scaling model. I call it a Monte Carlo scaling. A given impactor size will not always lead to the same crater size because there's intrinsic variability built into it. The surface, there's a default surface we create. It's called the icosphere. It's basically just it's the way of dividing up a sphere into equal size cells. This tells you how many faces and how many nodes on that cell, and then it gives you an effective size of the cells, 8 kilometers per pixel. It's not really a pixel, but the faces are roughly 7.6 kilometers, equivalent to surface area. The default target is the moon, and these are some of the parameters for it. And we haven't done anything, so there's current state is nothing's happened yet. Okay.
Question. My cell finished running, and because I'm on the remote machine, I want to download stuff because I'm anticipating that it might take some time. Should I just download both of these folders?
Yep. Okay. So let's take this apart. Each one of these things that's listed there is a component that actually can be used independently. So the other thing I've done is I've designed this so that you don't actually have to use this as a landscape evolution model. You could use this as a tool to do crater scaling. You could use this as a tool for plotting the velocity distributions of things. Each one of these components is independent. It can be used by itself, right? So I just want to show you an example. Let's look at the production function. So the production function, I said that the default production function is the Neukom production function. And I put a lot of description of what that does and how it works. If you remember, there was there's a paper in here that by Neukom that sort of is the one that everybody references. There's a link here, but I actually have it on my computer, so I'm just going to show it to you. And I'm going to show you a plot from that. In 2001, Base Sciences Reviews. All right. So the lunar production function is plotted basically in this nice plot somewhere here, like here. So you saw this from the talk that I had, right? So that's the size frequency distribution of the production function, right? And there's a corresponding the one that shows the time component of the production function. So right here, right? So one of the things I've done here is create an example where we make those plots. So here is, this plot was actually generated by Cratermaker, by the production model, by itself without any landscape evolution. And I tried to make it to sort of mimic the style of that Neukom plot. And it's a full script. So if you actually go to the examples page here, to the production function, you actually see these the documentation page are dynamic. They're actually generated on the fly when we build a release. So these are actually non-step. These are actually built. This was built this morning when I re-upped the version. So this is how we know if anything breaks, the examples will reflect it. So this shows you the model. Now, of course, with a landscape evolution model, the actual Neukom production function has a minimum size and maximum size that they fit. We need the larger and smaller sizes in order to actually do true landscape evolution. So there are these extrapolated bits that go large in size. So I've highlighted that in the dashed lines to show you these are the bits that Cratermaker just extends the Neukom model so that you don't have artificial truncations places. But you can see here that this right here imports just the production module, right? You don't actually have to run the simulation. You just run the production module out, And you'll notice that there's we create the production variable here with this. This is called a factory method. And there's a thematic thing going on where every module has a .maker factory method. It's how you create a specific instance of that model. So, so the Noika model is one type of production function. So you create it by calling production maker and calling the Noika model. And in this case, we're going to create a projectile model, so we can plot the projectiles that you're making. You can also do the moon, which is the moon creation is a Mars one. So moon, Mars, and projectiles are the ones. Everything is documented in the API pages, so you should be able to sort of look those up. In fact, let me do that real quick. I'll show you the API pages for production. So it shows you the valid options. There's right now we have Noika and a power law. So you can actually do pure power law production functions. There are a bunch of components to this, these methods that basically do things like go from number to age and age to number. So this could be really useful if you want to actually build isochrons or actually fit crater data. You could actually use this for tracking ages of crater counts. In fact, I'm building a lab for a class that's going to use this to do that. But you always instance it with the maker tool. So you'll see that over and over again if you look through the.
From a generated source or distribution of velocities and angles, sizes could be put that as an input and create a surface.
Yes, actually in principle, yes.
Basically from end body output.
Yes, I'm actually working on
Sure, that's
going in that direction. So basically, we're running up against, this is still a new code, so there's a lot of things I want to do I haven't done yet. So one of the things I would like to do is have like a tutorial. This is how you would create a custom production. This is what components you would need. Because all these tools are designed to be really modular and flexible, and you can basically build off of them. It's taken a while just to get the basic stuff done. So here's an example where actually my student Austin just graduated with this, helped me put this together. This builds basically a simple isochron for the moon and Mars using the built-in production tools. You can see they're both the production function, but one is the Mars one and one is the moon one. So you iterate over those and build two plots using the moon and Mars work in production. Okay. Okay, so let me that's just sort of gives an example of how you can invoke the individual modules on their own. Some of the modules are more useful than others by themselves. Morphology doesn't really make sense without a surface do things, but crater scaling is one that I'm also really happy about. So the crater scaling is how you go from impactor size to crater size. This is an example of I recreated a plot that was in this Paul Schenck paper from just a few years ago. And I basically recreate that plot with our Monte Carlo crater scaling law because we actually, like I said, each time you place a crater, you get or an impactor, you get a new crater scaling. And so there's a distribution in all the different parameters into it, so you can actually see how the transition diameter for simple to complex transition is actually a distribution of points. You do this 1,000 times and you'll get a slightly different answer, but they follow the distribution that was given by people like Schenck, his papers. You can do it. There's a more basic version of it that you can use. You don't want to do that. So again, if you go to the scaling module, let's go to the API page of the scaling module. The scaling module has the older CTEM scaling that we use, which is based on that whole sample scaling. Jim Richardson did a little tweaks to it, but it's a pretty straightforward. Really, the only difference between the CTEM and Monte Carlo is all the parameters, the empirical parameters that have distributions, uncertainties on them. We just implement those in Monte Carlo. Okay, any questions about those components? So if you want to use this tool as just for something for generating, for scaling craters, then you could certainly do that without having to know anything more about the simulation. But I wanted to show you some of the, did everybody get their cells run here?
They're still,
So chucking away.
they're still loading for me.
Did you get the first one going? The very first one, where you just did like a billion years? It's this cell,
It's a
so
number on the side that means it's wrong, so yes.
I did this one or, oh, I'm sorry. Yeah.
okay. So,
Yeah, okay, I did.
all right, so what we did here is, the simulation class is sort of a master sort of, when you invoke a simulation class object, it creates all of those modules, the morphology, the production, the scaling, everything gets instantiated. So you can actually pass arguments to this to change. If you want to do Mars instead of the moon, you just pass target equals Mars. So Mars instead of the moon. So the default is the moon. That's what we've done here. And what I've done here is I've run the simulation for I should say that the units, the fundamental units that we use are million years and meters. It's a weird set of units, but I find that million years makes more sense than years when dealing with cratering, because otherwise everything's this big floating point number you have to pass through. But it does trip me up even a little bit, but I think a million years is the fundamental unit of a crater problem. So that is certainly something that I could change if it becomes a user pickup problem. So you can always let me know if you think year would be a better. Seconds is right out. I'm not going to do seconds, so no SI, right? So I already had to decide meters versus kilometers. We decided meters because CTS. We're not going to do centimeters. That's right out too. Okay, so the run invocation basically runs a simulation. It creates a simulation object, and again, there's a bunch of these sub methods that you could actually evoke individually. One is to populate a surface. One is to add an individual crater. These are all happening. So this is the most basic way of doing it. So I'm going to run a simulation for a billion years using all the defaults. I'm going to output every 50 million years. I just made an update that means you don't have to do these. Worry about that. Okay, so this and this should have generated in this output folder a bunch of NC and VTP files, right? So let's see what we can do with this. So the basic file format that's where things are stored is netcdf, and it's accessed through a tool called UXArray, which is a version of XArray that is used for unstructured meshes. We don't have to worry too much about that right now, but I want to visualize this. So I'm going to have you all open up ParaView. Okay, so if you've got that run, I want you to go to File, Open, and you're going to want to navigate to wherever you have that output folder. I've opened it before, so I have it here. It's unfortunately ParaView uses some non-standard file. It has its own custom file navigator instead of using the operating system's one. So it's a little hokey. So it took me a little bit of time to sort of play around with it, but show me. Oh, it's the wrong one. Now, once you get it, when you find the folder, you'll notice that ParaView automatically sort of groups file names that have like a number appended to it. So I can actually show you that the surface VTP is actually 1, 2, 3, 4, 5, so on and so forth, right?
That's pretty.
So the reason for that is because you can actually click on a group and it automatically knows that this is an animation you want to do. It will actually create it as an animatable surface. So I'm going to open that up. Has everybody gotten this far? Please don't want to.
It's just taking forever to run, so I'm not getting these output files. I don't know if I'm.
You're the first simulation didn't run yet?
I don't know what exactly you mean by the first simulation.
There are 2 simulations that get run. Let me see. It should be cell number 4.
Yeah.
You have to. Okay, you did that. Okay.
Yeah, I started running it. I ended up restarting it for a few minutes ago because it just seemed to be like taking forever. But yeah, it says it's currently running, but it's not.
Okay, let me do this. this is a new feature I added, which I'm kind of regretting. Turn off that. Let's try this. How old is your laptop?
Sorry, I think 4 years old, it's not that old. Just,
Mine's been being real slow too, so.
yeah,
I don't know,
It's
just probably just have a bunch of things happening in the background.
it's the kind of issues that they.
Well,
one thing we could do is if you see, you might notice down in here that there's this grid level equals 7. So the default ISO grid, there's a formula that tells you how many grid cells. So ISO grids are like finite, fixed numbers of grid cells. But what happened to me? So where are the rest? What happened to all the rest of the cells?
yeah, I also only have first 5 cells.
Oh, you at least your first simulation finished, so you actually could open it up in peer review now.
I don't know what happened.
Huh. All right, so we want those situations too. We got it. Almost like hidden or accidentally deleted it somehow by scrolling. Should be weird. So. First, you don't succeed, restart.
Okay. I don't have like the red living stuff that other people have.
That's good.
Oh, I thought that was.
Oh, the red, yeah, that's not good. It's a red, when you say red, my thing is a bad thing, but that it's, I guess it's more pink than red.
Or, yeah.
Yeah, there's a way to make the format look better for Jupyter, and I just never implemented it.
Well, I guess like I just don't know why mine's not showing on that.
I don't know either. That's very strange. It's like it hasn't quite made it far enough to actually do it.
I mean, it might be Windows being weird. Mine was also like showing some, but not all, and like making separate
All
living
right.
things.
So why don't you just sit with somebody who's working, and then we'll kind of work on it. Okay, so
Like,
Yeah.
I love it.
when is yours, you were able to get up to the peer review?
Yeah.
Okay. So if you just click on so you click on Surface BTP, and I'm gonna hit that, it's gonna load that up, but it doesn't really do anything yet. So you can either, so basically peer review has, you've indicated peer review, you would like to put a file in, but it hasn't read it yet. So to read it, you either hit the apply button or this little eyeball button. And then it opens it up, and you see it's just a blue sphere. At least in my default settings. So not gonna show much. So what I'm gonna do is we want to plot the face elevation. I'm gonna click face elevation under the coloring. It's also because it's a time sequence, so it's scaled you can see that the color bar here goes from 0 to basically 0, 10 to the minus 38. So that means that it's scaled the color bar based on the initial surface, which has no elevation changes. It's a ball, it's a sphere. So there's a button right here that basically says rescaled data range to all time steps. If you click that, you'll get a little warning. Says that, are you sure you want to do that? This might take a while. And you say, yeah, that's fine. It's really not that big a deal. So, okay, we'll do that. What it'll do is it'll go through all of the files that you read in, and it will basically work out a minimum maximum scale for the entire range of data. So now you can see it's orange. So that's 0. And so you can see now it's, you can anticipate that there's going to be negative 4.8 thousand to 1.8 thousand, negative 5 kilometers to 2 kilometer long. Okay. So there's a fun little button up at the top, little play button. So if you hit play, you should start to see little dots hitting the surface. Those are craters. So you've made craters.
Cratermaker.
Yeah, so you've made craters now. All right, so you can kind of zoom in a little bit and kind of see the isogrid surface divides things up into these cells. So that's the actual surface representation are these basically it's a mesh full of uniform cells. There are a lot of options for doing different kinds of surfaces. If you have some time, I'll show you the high-res local, which is my one for making those tiny patches on the surface. There, we've made craters. There's actually some great tools for changing the coloring. So I like Viridis, that one.
Can you say one more time what you did to change the color or stretch?
Oh, there's a little button. It's right here. It's hard to read, but it's like an arrow going left and a exclamation mark. It says rescale to data range over all time steps. Should be right underneath the
Okay.
coloring and edit.
And I don't have the color map editor open on my side, so I don't know how to.
Oh,
open
yeah.
that.
So how did I think if you click edit, this edit button right here, it opens that up.
Good.
Yeah.
You have to click the play button up there.
Oh, I see. It's because I only have one image.
There it is.
Oh, wait.
No, you do. You have it. It's just loading at a time.
Because it.
So click the little, you can also click the end button that takes you the one to the right of that. Yeah, that just takes it to the last frame.
This file, like,
All the
Sorry.
files. Yeah.
oh,
Yeah, it loads up basically the first file and then it loads up all the others as the time steps.
okay, I kind of don't understand how I have that.
Well, it's loaded up whatever it's got, so
Okay,
it's got,
so this is-
so if you reload it and tell it, look for more new files, it'll keep appending to the thing. So you can see the intermediate results as we go. Because sometimes when you actually do real production runs, it could take like days to get these things done, so it's good to be able to see
Where you're at,
where
yeah.
you are, yeah. All right. Everybody who's got their thing working has gotten this far at least?
Yes.
Okay, you're, same thing, thought you were doing great. Okay, what's going on?
Started loading it.
And mine's just taking forever. I probably have too many other things open.
Okay, all right. Let's try opening that again.
No, mine's a phone number.
Okay, let me see if I can navigate it.
Oh,
Okay.
And mine's being really slow too. I don't know what the issue is.
Something
I'm
like.
good using people's computers. Or on mine.
I don't know.
Open.
I've used Cratermaker before though.
Oh,
You've used this.
I haven't used it. I haven't used the simulation part.
Oh, I see. Something
How did you come across it?
the reader could not be found.
Just
That's weird. Is that that was old P files that pair reviews?
Yeah. But yeah, I've been using it for my
Huh?
Have you shown it?
later project. Now that I know.
Which is VTK. Okay, that's weird.
But yeah, look, craters have been made.
Those are not spherical.
It's a lot of craters. There's like 1,000 craters in this area. Or 3,000 actually.
Yeah.
But yeah, basically trying. Insane.
It never occurred to me that you wouldn't be able to read VTK because the same company makes these tools, and so I thought that was their
I'm using it.
their own file format. So why would it not be able to VTK?
Thanks.
Polydata. It's right there.
There's my terrain.
It's on my plotlet.
Yep.
Can't find polydata element. I wonder if did something get corrupted.
Yeah, the mantle elements doesn't look right, but or at least it doesn't look.
Okay, let's try
run it again.
run it again.
Whether it looks right is
So
Looks like something.
this is why these are always fun to see the things that happen to other people's computers that didn't happen to mine for some reason.
The hope is that ultimately I'm gonna make this look. Whether that's actually gonna happen or not, for me to be thinking.
Stuff with that. hopefully that starts to do something.
Yeah.
All right, so there were two simulations that ran. One was this where it's basically pure Monte Carlo. You're basically just, you're running a production function. It builds some random craters, pulls from a distribution. There's also there's another way to do it. My student, Austin, has been using something in CTEM called quasi-MC, quasi Monte Carlo, where the larger craters are real, like they're placed in the right position, and then all the smaller craters are randomly in place, so that we can actually do things like find out like what do apollocytes, what kind of material do you expect to see at apollocytes? We just had a paper published on that, just came out. JGR planets. So I am demonstrating here basically a way in which you can place the craters manually. So, like I said, that there are these components to Cratermaker that are independent. So there is a crater module that's independent. And I'm going to go show you what the crater module looks like, because this is actually, I think, a really powerful tool for doing things. The crater module allows you to create a crater and at the same time, everything about that crater that you could want. So let me find the crater box here. Okay, so you can, when you invoke a crater through the crater.maker, this is why I call it .maker, so I could have crater.maker as the thing, Cratermaker. If you invoke crater.maker, the only thing you need to do is you need to give it a size of something. Once you give it a size, reasonable defaults will fill in the rest for you, okay? So there are a number of ways that you can actually decide how you want to describe the size of the thing that's going to be made as a crater. The one that you're going to probably, that we use the most is just define the final crater diameter size. That's the diameter of a crater is the final diameter. You can also specify radius if you'd rather work in radius. And they're mutually exclusive. You only do one of these things. You could also, if you want, you could import the transient diameter. This is why we make it we don't just say diameter. You have to say is it as a final diameter or it's a transient diameter. So you can import it. You can basically describe the transient diameter and it will compute the final diameter for you based on the scaling relationship. Same thing with radius. And all the diameter things have a radius companion. You could also define a projectile diameter and it will define the projectile and build the crater the right size for you. Same thing with projectile radius, and you can even put the projectile mass. Your projectile model should have a density component to it, so it will do all the scaling for you. Okay, so and once you create a crater, it creates everything else. So if I was to create a 100-meter crater and I print that crater, you'll see that it's automatically computed the transient diameter, the projectile diameter, the projectile mass, and it's going to report the density because that's the model that's used. It will give you the velocity that used in the scaling. The default projectile module uses a distribution of velocity based on a source population. So that tells you what velocity it used.
But if you ran this 100 times, those values would be different.
In fact, let's do that real quick. I'm just going to copy this into my notebook and do that in real time. Okay, so I'm going to scroll down here. That already imported that. So yep. If I do it again, but look, that's 17.9 kilometers per second, 15.8 kilometers per second. So you can start to see how you could use this as a tool to get, invoke this a gazillion times. So in the example scripts we have, we do that. Just like you call crater, you make a crater a gazillion times and you figure out what the velocities were, build the velocity distribution. Right? We also do things like the impact angle direction. Now those are not used currently for much. The impact angle is used to modulate the scaling. We're hoping to, when we get the more sophisticated morphology function and the secondaries and ejecta modules, that we'll actually use these direction things to actually modify the morphology of the crater to reflect the direction of the impact and the ejecta direction of impact. We haven't gotten there yet, but it's on the to-do list.
So that apply itself both in ellipticity of the crater and
And the ejecta.
ejecta blanket.
Yeah, yeah.
That's cool.
Yeah, it's not implemented yet, but we're sort of working. I have a funded an LDAP to actually do a bunch of this stuff. Next 2 years, so
And-
working on it.
The argument final diameter into Cratermaker, that's one option. Is there can you forward model this from velocity and angle?
Yep.
Okay.
All of these parameters can be input manually if you want. So you can override. So there, like I said, my philosophy for this is that you invoke everything with reasonable defaults with very few required arguments. The code will use some reasonable model for how to fill in the blanks that are based on typical use cases. But everything is overridable by the user. So what I wanted to do is I wanted to make it so that a person could start using this without having to know I need 20 different arguments to pass, or I need parameters for anything. Just get you started. I give it a diameter, it gives me everything else. And then once you're like, okay, now I need to use this for Europa. Now I need to sort of use the Europa things, right? Instead of the moon things, right?
Yeah. So what if I give it velocity, angle, and projectile mass?
Yes. So let me show you the API for Crater. So these are all the, let me go to the Crater.maker. I sometimes even myself forget to use the maker method and not just invoke it. So you can pass to Crater, you can pass a scaling model. So either a string name that can identify a built-in string, like a scaling model, or you invoke a scaling object and pass the scaling object in. Same thing with the target. You can call up a target. You could put in quotes Europa as your target, or you could create a Europa target object and pass that in. If you don't pass anything, it does the moon. Same thing with projectile. And then you have all the different other options: final diameter, radius, blah, blah, blah. You can actually send the velocity in. You can send the mean velocity, and it'll draw just from a distribution velocities instead of just a specific velocity. You can define just the vertical component of the velocity, and it works out the rest from the angle.
The distribution, is that uniform or Gaussian?
Yeah, it uses a okay, so the way, remember how it does it is the mean velocity. It depends if you pass the mean velocity as part of the projectile or through here. Because I think that what it will do is it'll modify it based on the escape velocity. It will basically fit it within escape velocity. But there's an example that goes through that. I don't remember exactly which way I went. I think that because you can define these things in the projectile module, and the projectile module assumes a heliocentric population, so it basically uses the velocity as your encounter velocity, and then it uses this Viva equation to actually work out the surface impact velocity.
Yep.
So it never gets higher than the escape speed, and right?
Yeah.
It's or it never gets lower than the escape speed. But I think you can when you do it here, it just uses a Gaussian.
Okay.
Yeah. Okay, so there you have a lot of things you can pass in here, right? You can even pass there's a Monte Carlo component, so you can actually it'll instantiate its own random number generator. But if you want to have more control over the random number generator, you can pass one in. That way you can have more reproducibility if you wanted. So the second example that I built, where we build the real craters, kind of illustrates how to do this. One application anyway. So what this oman3.csv file is a database of craters that from an LPSC abstract from a few years ago. This is just a list of named craters, their final diameters, their positions on the moon, and they're roughly in order of age. It's not perfect, but it's kind of, we know South Boykin is the earliest one. I think they're just kind of grouped into, late Imbrian, Radicinian, Copernican, late Imbrian, pre-Nectarian, yada yada. So you got a bunch of pre-Nectarian craters, and then they go on. But these are all the named craters on the moon. So it's not a comprehensive list of craters, but it's the ones that have names, and it's 8,600 craters. So what we're doing here in this is we're reading that in with pandas. So I've also, one thing I did was I created a lower resolution grid to make it run faster. The way we're not spending 20 minutes waiting for this thing to run, we're already waiting too long. And then we're going to loop over the craters in that population, and we're going to emplace them manually. And the way you can do this is you can use this emplace tool, and the emplace tool can actually emplace a batch of craters all at once. So you can actually like batch up. In this case, we're going to batch up about 500 craters at a time, and we pass that into the emplace function. And it's intelligent enough that it will actually emplace craters simultaneously as long as they don't overlap each other. So what it does is it actually evaluates how much of the terrain is going to be modified by that crater, and it queues up all the craters that don't overlap each other, and then parallel basically emplaces them all on the surface, and then it goes on to the next. That way that the craters, it's an efficient way to get the craters to happen in the right order without having to wait one at a time. So if you have two craters that don't overlap, so it doesn't really matter what order you place them on the surface, it just places them at the same time. Does that make sense? Okay.
Okay, so you're creating this, you're iteratively going through the CSV and creating this list of craters.
Yep.
Using your Cratermaker. And then you pass every once in a while, so every 500 steps, you pass that list to the sim. And yeah, you pass it to the emplace function. And it checks, or it does and then you're just saying that the emplace function is hastened or is made faster by trying to put as many craters on the surface as possible that aren't overlapping.
So it's trying to go in order. So it starts with goes through the list in order in which you appended to the list.
Yeah.
And the first one that happens is South Lake, and South Lake affects the entire moon, so it goes by itself. And then it will say, okay, the next like 10 craters, it checks to see what are the cells that are going to be affected by that crater, and as long as that crater and the next crater don't overlap any of the others previously, it goes as far as it can until it hits the first time a crater is going to overlap one from that batch, and it batch processes this, and then it keeps going through the list. So it's a way of sort of before I did this. Creating this talk took about several times longer than it does now. So it's actually really more efficient.
Why not just make the crater list in one loop and then just call sim in place on the entire crater list?
That's what it's doing. Yeah, that's what it's doing. It's just behind the scene. Oh, why that?
Like,
oh, wait, yeah. That's how we can make a movie. Yeah, you don't have to do that. That's how we can make an animation.
Oh,
yeah, so that's just I divided it arbitrarily so that we can have little steps we can animate it. So if I open up the real crater output, okay. Oops, supposed to. Same thing. We're going to go to elevation, scale it. See, and actually, there were 19 steps, and if I click on that button, that's the near side of the moon. So Imbrium, that's Sinus Iridum, Serenitatis. I think that's Nectaris. I get my lunar geography. I think Oriental is right here. Oriental, Aiken, Schrödinger is down there. So these are all the craters on the real moon. And because I did them in little 500 chunks, so every 500 craters you can actually, watch sequence. Of course, most of the craters are the Imbrian small craters. So you could subdivide that even more to make it even more like, more pieces. So we can go step through it. We say, okay, what's the first? So we had SPA, and then there's some more. Okay.
doing crater morphology right now? Like, is there just a simple and complex? shape, or
Yes,
is there
okay,
a-
yes, right now, the morphology, you can see that the complex craters are not complex, right? Right, they're very much simple. So this is based on the CTEM's morphology model, which I had an LDAP that just wrapped up. Actually, I'm supposed to write the final progress report this week. My postdoc Junju worked on a big project where we did a big analysis of crater morphology to work out an empirical model that described the morphology. In fact, I showcased one of his results here in the user guide, but it's not implemented yet. The paper on this, he just returned the review of it, so I'm waiting for the paper review to be done. So the craters are going to look a lot more realistic, especially complex craters. We haven't done the central peaks yet, but we've got the more complicated, and this is all based on data. So it's all basically based on what real fresh craters, sort of textures and their distribution of like shapes and things look like, just not quite implemented yet. So the simple moon morphology model, which is the default, is the one that's based on CTEM, which is pretty good for simple craters at really like Mare scales. It starts to look really unrealistic at larger scales, but that's one of the very first things going to be corrected this year. Once that paper is accepted for publication, we'll start implementing his model. He had to do some revisions, quite a bit of revisions on that paper. So it did change things a bit. So I was waiting for that to finish up.
Do you feel like morphology is going to be a bit of a rabbit hole in terms of like lunar morphology may be quite a bit different than I see moons?
Yeah,
and like
Not so much a rabbit hole, but because the techniques that he developed as part of our project can be applied to other places. You just have to do the analysis. We gave basically have a roadmap for how to do it. It's using topographic spectral analysis. So if you wanted to create a morphology model that matches what we've done for like Mercury or Europa, whatever, all you need is to basically collect the kind of data that we collected, and then you can run it through the model and get the coefficients for the different morphology parameters, and then we can implement that. So it's not a trivial thing to do.
will it be able to just like Valhalla or something like that?
Yeah. That's the long-term, there's a lot of long-term goals that I know we will be able to, it's a matter of the time it takes to actually do them. This is why I'm bringing this out to show you all, because these are all things that we could use help with, Willie. Or not, USB users.
Should get some video game producers to know about this, because they could start generating the
More realistic looking surfaces,
more realistic surfaces that are being
there's a type of surface I'd like to show you. Okay, the surface user guide actually describes some of the sort of the details of how the surface is being built. But we actually, there's a special surface type. So that the default is the icosphere that kind of looks like this. But there are other surface types that you can do. And this shows you like the grid level, what the grid level means as far as like resolution, right? So the default grid level is 8. That's this. For the example that I showed of the Omen database, I went down to 7 just because it's, it's a little faster. It's a little cruder, but it's good enough for this demo. You could also have this arbitrary resolution, which you could, if you wanted to have full control over, I don't want to have a surface that's in one of these boxes. So you can have an arbitrary surface, but it's just messier looking. Like you can divide a sphere into cells of equal size and anything other than the icosphere sort of numbers. It's just a geometric principle, but you can do it, and it just makes a messier looking grid. The one that I been starting to use more and more is this high-res local. Okay, so I showed you the CTEM simulations where you're looking at a little patch of Mare for 4 billion years. One of the things I learned from doing CTEM is that you can't actually model a cratering on a surface in isolation, because cratering has this property that everything at all scales matters. So a surface that's 100 meters on the side is being affected by craters of 1 kilometer and 100 kilometers far away. So we dealt with this with CTEM with this sort of hokey thing I call the super domain. It sort of quote unquote creates craters outside your visualization domain, but only just in places the ejecta and does things from without actually placing the crater. What Cratermaker does is it always builds a full sphere. So you don't model a patch of the surface. You basically model the entire sphere. But if all you care about is a little small, like, in this case, 5 kilometer radius, a patch of the moon, you can actually create a high resolution sort of local region that then grades into lower resolution as you move away. So that we actually emplace the craters outside that domain, but we don't care about those craters. They're just there to like be a place for craters to form. And the scaling of those cells is set so that the smallest crater that you could model on that terrain, basically the size of the cell, is the crater that's just big enough to reach my domain. So it goes from, basically more fine scale to really rough at the antipode. So only the largest craters can form there that can have ejecta that can make it all the way to your domain. And so that's the kind of surface you could use to actually make like a high resolution local region of simple craters.
Sounds like it's on its way to adaptive mesh refinement.
It's sort of a poor man's adaptive mesh refinement. It's an adaptive mesh that's not refined.
Yeah.
Right. There's no, I wouldn't know. I don't think there'd be a good way to do a true adaptive mesh refinement on this because, so the problem is that, and there's a lot of work that went into sort of generating craters of the right sizes. Because if you, the total number of craters on the entire moon, if you were to do like it's like a couple meters pixels, it's like, billions and trillions. So you don't want to model this. So we only model the really small craters in one little tiny region. And then as you move away, you only model the larger craters. Okay, so we're just about out of time. I forgot last time that there's a survey that Rosie wanted you all to do. Did you all get an email of that? Okay.
Not yet.
Let me pull that up and I'll you all were in my one yesterday. My emails. Okay. There's a PowerPoint she gave me that actually has QR codes on it.
Are you using Chrome as your browser?
I use Chrome when I use Google stuff, and my Google Sheet is in Chrome. So
Just because if you open those survey links in Chrome, you should be able to. There's a quick way to generate.
yeah. Yeah, I don't have a way to contact you all directly. So wait, here we go. Survey QR. Oh, okay, it's in this email. I just didn't see that. Oh, there it is. Okay. I didn't. Okay, there we go. Okay. So Cratermaker. So there's the survey. She wants you to fill this out. So if you've done this today, please go here, fill this out. And for the three of you who are here for Swiftists, I'll show you that one too. Okay. You got that? Okay, here's the QR code for Swiftists. Mr. Day. All right, so we basically scratched the surface of Cratermaker. I didn't even get into the piling local with Rust. It's a lot easier at this because we use Rust instead of Fortran. It's I have my son to thank for that. I'm still learning Rust. I'm not good at it yet, but apparently neither is ChatGPT. It's not very good at Rust either. So I'm actually have to learn. I can't vibe code it as much as I intended to. So I'm still learning that, but it's much easier to compile a version of it because Rust just works like Fortran, which takes so much effort to get working. Is there anything else that have curiosity in your mind or anything I could address?
Apparently, Gabe has been using Cratermaker already.
Oh, you have? Really? Okay. Cool. I know there's somebody at Goddard who's also I've been helping with some. They're using it. They're actually showed him how to do the high res local terrains so that he's making like calibration targets for some instrument on LRO. It's been fun to see more people using it.
So far, I've mostly just been using the generation stuff, like just getting a very convenient way to get a list of randomly generated craters.
See, that's been one of my goals, is that it's so hard sometimes to even get the basic things, like I need to generate a production function and I have to go and find the script that does it, does this. So I have a one-stop shop for the basic crater scalings, production functions, everything. Might actually have. It takes a while to run those high-res local ones, so I didn't prepare one for this, but you know, if you want to reach out to me, and if you have any other questions you want, like if, for instance, if you say like, you know, I'd really like to be able to do X, and it doesn't do that yet. Oftentimes I can like implement it in a day. It's like something like it's really useful. So just reach out to me, and I can even show you some more examples and some of the other things that we've done with it.
Sounds good.
And so, yeah, more people using it, the more happy I'm. So, and NASA, you know, NASA funded me to do this, so return on investment if the students are using it. All right, thanks a lot for coming.
Thank you.
Thank you so much.